Hello there. In this video we're going to discuss what is called the Somos Quadratic Recurrence constant, which is given by or represented by the letter sigma, which is defined to be equal to the square root of 1, square root of 2, square root of 3, square root of 4, and so on, where all of these are nested radicals infinitely many times. So we'll describe how to prove the existence of this function and also some interpretations and representations of this function as well. Okay, so the first thing we need to do is establish the existence of this constant by proving that this sequence converges. So let's go for that. So let's go to prove that this constant exists. So what we're going to do is we're going to begin by letting x be equal to this representation. So we're going to prove that x is a real number. So in the case that f does exist, then we know that x must be greater than 0 because it's the output of a radical. So what we're going to do to begin defining this sequence, so we're going to define a1 to be equal to the square root of 1, which is 1. And then we're going to look at a2 to be equal to the square root of 1 times the square root of 2. Which is the same as the square root of 1 times the square root of the square root of 2, or 1 to the 1/2 times 1 to the 1/4. So if we continue in this fashion, a3 will be equal to the square root of 1, square root of 2, square root of 3, or the square root of 1 times the square root of 2 root 3, which is the square root of 1 times the square root of 2 times the square root of, let's see, it should be the square root of the square root of 2 root 3. So that's going to be the square root of the square root of 2, and then the square root of the square root of the square root of 3. So we can rewrite that as 1 to the 1/2 times 2 to the 1/4 times 3 to the 1/8. And then we can slowly get a pattern for this. So a4 will be equal to 1 to the 1/2, 2 to the 1/4, 3 to the 1/8, and 4 to the power 1/16. So these powers, so this is going to be 2 to the first, this is going to be 2 to the second, this is 2 to the third, and this is 2 to the fourth. So notice these numbers correspond to the number for which the base corresponds to. So that's a good property. So we can say an is equal to 1 to the 1/2 times 2 to the 1/2 squared times 3 to the 1/2 cubed times all the way up to n to the power 1/2 to the n. Alright, so from here, what can we do? So since an is greater than or equal to 1, which is of course greater than or equal to 0. And this is going to be true for all n in the natural numbers. So how do we know that that is true? Well, the first one is equal to 1, and the next one is going to be the 4th root of 2. So the 4th root of 2 times 1 is going to be the 4th root of 2. And the 4th root of 2, in case you don't know, is 1.189. And if I consider, say, 3 to the power 1/8, which is going to be the 8th root of 3, that's going to be approximately equal to 1.147, and so on. So as we see, as we increase the value of n, this number increases. So this number is always going to be greater than or equal to 1, so no big deal there. Alright, so clearly this is an increasing sequence, in a way. So with this in mind, what are we going to do? So now I'm going to take the natural log of an. I can do this first off because this number an is always greater than 0. And also, this number is also bigger than 1, so the natural log of an is also going to be positive as well, or non-negative actually. So the natural log of an is going to be the natural log of 1 to the 1/2, 2 to the 1 over 2 squared, times all the way out to n to the 1 over 2 to the n. So we can rewrite this in another way. This is just the natural log of an is equal to the natural log of the product from k is equal to 1 to n of k to the power 1 over 2 to the k. So as we know, the natural log of the product is equal to the sum of the logs, so we can rewrite this as the natural log of an is equal to the sum from k is equal to 1 to n of the natural log of k to the power 1 over 2 to the k. So keep in mind, this is an exponent of the parameter of logarithm, so he can be withdrawn down. So we have that the natural log of an is just equal to the sum from k is equal to 1 to n of 1 over 2 to the k times the natural log of k. Or moreover, the natural log of an is going to be equal to the sum from k is equal to 1 to n of the natural log of k all over 2 to the k. And this is something we can work with. So what we're going to do is we're going to consider the infinite series, the sum from k is equal to 1 to infinity of the natural log of k divided by 2 to the k. So what do we know about this series? So this series can be proven to be convergent. So this converges, and one easy way is to look at, say, the ratio test. So the ratio test. You can easily use the ratio test because the bottom is an exponential and the top is a logarithmic. And by our dominated convergence theorem, we know that, our logarithmics are there, our linears are there, and our exponentials are up here, which grows faster than quadratics if the value is big enough. So this definitely will converge. So this is extremely useful for proving the convergence of the limit of this series. All right, so from here we have the following result. So that means the limit as n goes to infinity of the natural log of an is equal to the limit as the natural log of infinity of the sum from k is equal to 1 to n of the natural log of k all over 2 to the k. This expression is independent of the value that we're limiting, so we can just apply the limit to the upper bound of the sum. So we have the limit of an of the natural log of an is equal to the sum from k is equal to 1 to infinity of the natural log of k over 2 to the k. So if that's the case, then we also have that the natural log of the limit as n goes to infinity of an is equal to the sum from k is equal to 1 to infinity of the natural log of k to k. And we've already proven that this series converges, so this is going to be a finite number. So if that is a finite number, then we can exponentiate both sides of this equation. So that means the limit as n goes to infinity of an is going to be equal to e to the sum from k is equal to 1 to infinity of the natural log of k to the 2k. So if this sum is finite, the exponential of that sum will also be finite, so this expression here is also less than infinity. I'm going to call this number sigma. So this is Somos' quadratic recurrence constant. So Somos' quadratic recurrence constant. So therefore, what do we have? So sigma is going to be equal to e to the sum. So that means we have like e to the alpha plus beta plus gamma plus and so on, which we can decompose into e to the alpha times e to the beta times e to the gamma times and so on. So it's going to be a product of exponentials. So that means sigma is going to be equal to the product from k is equal to 1 to infinity of, what do we have here? So it's going to be e to the natural log of k all over 2 to the k, which is the same thing as the product from k is equal to 1 to infinity of e to the power natural log of x to the power 1 over 2 to the k. So of course, these things cancel, and then we have our traditional representation for sigma. So sigma is going to be equal to the product from k is equal to infinity of, that should be k, of k to the 1 over 2 to the k. So this is, of course, equivalently the square root of 1, square root of 2, square root of 3, square root, and so on. So we've proven that this constant definitely does exist. And by computing several hundred terms of this, you can find that sigma is approximately equal to 1.66169, and so on. All right, so let us derive just one other property. That is a little bit more interesting to look at. So sigma, as we already know, is going to be 1 to the 1/2 times 2 to the 1/4 times 3 to the 1/8 times 4 to the 1/16, and so on. So if this is true, then what is sigma squared going to be equal to? So I'm going to square all of these terms. So this is going to be 1 to the 1st times 2 to the 1/2 times 3 to the 1/8, no, 3 to the 1/4 times 4 to the 1/8 times and so on. So as we already know, sigma, since it's a non-zero number, can be represented as sigma squared over sigma. And this is true since we've already proven that sigma is always greater than 0. So there's no division by 0 tricks here. So sigma squared is going to be 1 to the 1 over 1, 2 to the 1 over 2, 3 to the 1 over 4, 4 to the 1 over 8, and so on, all divided by 1 to the 1/2, 2 to the 1/4, 3 to the 1/8, 4 to the 1/16, and so on. I'm going to ignore this 1 over 1 term since it's just equal to 1, and I'm going to focus on the powers that are alike. So I have, instead, sigma is going to be equal to 2 over 1 raised to the 1/2 times 3 over 2 raised to the 1/4 times 4 over 3 raised to the 1/8. Next will be 5 over 4 raised to 1/16, and so on. All right, so what do I have here? So I'm going to represent this as 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, and so on, just as before. So I have sigma is equal to 2 over 1, 1 over 2 to the 1st, 3 over 2, 1 over 2 to the 2nd, and then 4 over 3, 1 over 2 to the 3rd, and so on. So notice my bottoms are the same for all of these, and the top is one more than those. So I'm going to represent this as the product from k is equal to 1 to infinity of k plus 1 over k raised to the power 1 over 2 to the k. So from here I can simplify this by dividing k into each of the terms, so k over k plus 1 over k. And I get this alternative representation for the Somos recurrence constant, namely the sum from k is equal to 1 to infinity of 1 plus 1 over k to the power 1 over 2 to the k. And I find this representation very simple because fairly interesting. Almost looks like the exponential constant, except the exponent goes to 0 instead of infinity like the exponential constant does. But, you know, it looks a little bit similar, so I find it interesting. So that's just some basics of, or the introduction of Somos Quadratic Recurrence constant. It definitely can probably come up in several other infinite recurrence types of problems. And also this is also a basic introduction on manipulations of infinite sums and also infinite products as well. Hope you enjoyed.